Hey folks, let's get started here. We're going to begin Calc 2 by looking at region between curves. So in Chapter 5, we approximated the area of a region below a curve and above the x-axis. We did that approximation by slicing a region into small rectangular strips. And then we found the area of each rectangular strip, and then we added up all the areas. We added them all up. It gave rise to what was called a limit of a sum. So what I'd like to do at this time is I'd like to head to the chalkboard to just review the process, review some old vocabulary, and introduce a new vocabulary term. So here I go to the chalkboard to do all of that. Okay, as I said, here's a quick review of what we would have seen in Chapter 5 back in Calculus 1, the whole process of integration. What I have on the board is just the graph of some generic function f. Don't know what it is, don't care. On the closed interval a to b. And remember, the process of integration was one where we sliced this region that was below the graph of f, above the x-axis, and between x equals a and x equals b. We sliced it into thin rectangular strips. Found the area of each one of those rectangular strips, and then we added them all up. So in summary, one of the things to remember to get across is this process of integration is generalized as slicing it into smaller pieces and then adding them all up. And that gave rise to, I'm going to write it over here, the definite integral. So the definite integral from a to b f of x dx. And I define the definite integral to be the limit as norm approaches 0 of the sum I equals 1 to n f of c sub I delta x sub I. Yeah, I use a little different notation than what your book would have used back in Chapter 5. Your book was into using like subscripts of k and then putting like a star in an exponent position. It was just a little too busy for me. So let's review what, my definition is the same thing as the books. It's saying the exact same thing. Norm is the length of the longest subinterval on the interval a to b. So when the length of the largest subinterval goes to 0, the sum from I equals 1 to n of f of c sub I, okay, now c sub I is any value in the ith subinterval. So you could pick any value in a subinterval and evaluate the function at that value, that's c sub I, and that gives you the height of a rectangle. Delta x sub I is the base of the rectangle. So height times base is area. We're adding up all those areas. We're taking the limit. It's a limit of a sum. Please remember, the definite integral is a limit of a sum. Some things that you may have seen back in Chapter 5, if not, this would be a new vocabulary term, is something that's called a regular partition. Okay, a regular partition is nothing more than taking the interval a to b and splitting it into n subintervals where each subinterval has the same length. So each subinterval would have the same length. That's what a regular partition is. If you have a regular partition, when norm heads off to 0, then n is heading off to infinity. And you can think of n as being the number of rectangles. This is only true with a regular partition. One more new vocabulary term that I'm going to talk about is there's a lot of rectangles in here. What we're going to get into the habit of doing right now in this section, and it's going to be so important for sections 6.3 and 6.4 as well as the future, is we are going to sketch just one rectangle that represents all of those rectangles. And we're going to call that rectangle the representative rectangle. So what I'll be doing in the future, now I'm not going to erase all of these here. What I'll be doing in the future is I'm just going to sketch in one rectangle, and I may stripe it like this. And that one rectangle represents all of the rectangles that would be in the interval A to B. And I generally label the representative rectangle. When it's a vertical rectangle, I tend to label it with a delta x. And then the height of the rectangle, well, it's below f. I can just arbitrarily say right now it's f of x. And this kind of reminds me that the integration process is taking the height of the rectangle, multiply it by the base of the rectangle. That gives me the area of the rectangle. So f of x times delta x reminds me an awful lot of f of x dx. So that's a review from what we saw in Chapter 5. One important new vocabulary term, the representative rectangle. So let's head back to the slides and see what we're going to talk about next. All right, so what we saw there, the process of slicing into smaller pieces to give us an approximation, then add them all up. I mentioned that was at the core of the integration process. And you're going to see this process throughout the rest of this chapter. Please remember that we can draw a single representative rectangle, one rectangle, to represent all rectangles that would result from the slicing into smaller pieces concept. It's much easier to focus on just one rectangle and apply it to all of them. Now the representative rectangle, it's going to be really important for topics in the next two sections. This is when we're going to start finding volume of solids of revolution. It's also going to be important in this section. In this section, we're going to use the representative rectangle to help us determine the area of a region between curves. So with this time, I'm going to head back to the chalkboard to kind of review old area questions and to see how it is we can find the area between two curves. All right, hey, in this example, what we're going to do is we're going to review some old stuff and we're going to discover something new. So over there, I have the graph of two functions, f and g. And I've indicated the interval there as a to b. And in part A, I say let's write a definite integral for the area of the region that's below the graph of f, but above the x-axis, between x equals a and x equals b. So that would be the area of this region here. Well, we know a definite integral can be used to represent the area of a region, and quite simply, the definite integral for part A is the integral from a to b f of x dx. All right, in part B, the same directions as part A, except here we're going to write a definite integral for the area of the region that's below the graph of g above the x-axis and between x equals a and x equals b. So for part B, it's just finding the area of that region. Writing a definite integral that would find the area of the region below the graph of g, above the x-axis, between x equals a and x equals b. Quite simply, that definite integral is just the integral from a to b, g of x dx. Okay, now part C. Write a definite integral for the area of the region that's between the graphs of f and g on the interval AB. So here, we're trying to come up with a definite integral that represents this region here that's between the graphs of f and g on the interval AB. And quite simply, this looks like simple subtraction will take care of it. We take the area that's below the graph of f and subtract off the area that's below the graph of g. So the area that's below the graph of f, That's the integral from a to b f of x dx. Subtract off the area that's below the graph of g. Well, that's what we did in part b here. That's the area from a to b g of x dx. But the directions say write a definite integral, not two definite integrals. So simple subtraction gives us what the area is. The single definite integral, using properties of definite integrals that you saw back in chapter 5, you can rewrite this as the single integral from a to b f of x minus g of x dx. And that's the definite integral that would represent the area that's between the graphs of f and g on the interval a to b. And in general, that's how we find area between curves. So, you know what, I'd like to generalize this just a little bit. So, let me erase the board and just generalize what we did here. Going to get a new graph up here. And let me get a new fresh graph. So here's the graph of f. Here's the graph of g. Here's the interval a to b. We want to represent the area of the region that's between f and g. And as I've already said, the importance of a representative rectangle. So let me put in one representative rectangle that would be in this trapped region. So here is that one representative rectangle. The base is delta x. Now I need to represent the height of that one representative rectangle. Well, we know the distance. We know the distance from f to the x-axis. That's given by f of x. The distance from g to the x-axis is given by g of x. So that means this distance here, the height of the representative rectangle, must be simple subtraction, f of x minus g of x. And so if you think, the area of this representative rectangle would be f of x minus g of x, its height, times delta x. Add up all the rectangles that would be in that region. Take the limit of a sum. That's our definite integral. So it's the integral from a to b, f of x minus g of x dx. So now, of course, if this were called g and this were called f, everything would be reversed. So rather than writing down a different looking formula or process or way of doing this, let's look at the relative positions of function f and g in relation to this representative rectangle. Notice, no matter where I place that representative rectangle in the interval a to b, I mean, I put it here, if I put it over here or over here, it doesn't matter. No matter where I put that representative rectangle, function f is the top curve for the representative rectangle. Function g is the bottom curve for the representative rectangle. So even more in general, I can think to get the area between curves, I integrate from a to b, the top curve minus the bottom curve. So that way, it doesn't matter what the top curve is called. It could be called f of x or g of x or h of x or just simply y, and the same for the bottom curve. But in general, we're integrating the top curve minus the bottom curve. And that's because no matter where I put that representative rectangle in the interval a to b, this would always be the top curve, and g would always be the bottom curve. So let's head back to the slides and see what is next. All right, so what we've seen that to determine the area between two curves, we can simply integrate from a to b the top curve minus the bottom curve, dx. And that's when we're using a vertical representative rectangle. Now, obviously, in order for us to see which curve is the top curve and which curve is the bottom curve, we're going to have to make a graph. Fortunately, we have graphing calculators, so that shouldn't be too bad. So here's the general process that I would follow to find the area that's between two curves, or area bounded by two curves. The first thing, sketch the region. So I could use my graphing calculator, but then from that I would sketch it onto paper. Sketch the region. And after you sketch the region, and you see what region it is you're trying to find the area of, put in a representative rectangle. Label the base of the representative rectangle and determine the height of the representative rectangle. Once you've done that, it's short order. You can write a definite integral that would find the area in question. Now, points of intersection may need to be found in order to determine the lower limit of integration A and the upper limit of integration B. And then once we have all that done, we just simply integrate and use the fundamental theorem of calculus. So let's check out this example. We're going to find the area of the region that's bounded by the graphs of f of x equals x plus 2 and g of x equals negative x squared plus 4x plus 2. So you should have been taking notes up to this point in time. You should definitely put this example in your notes, write it all down, get the example in your notes, because I'm going to head off to the chalkboard and I'm going to work through this example. All right, in this example, we're going to determine the area of the region that's bounded by the graphs of f of x equals x plus 2 and g of x equals negative x squared plus 4x plus 2. All right, so to review, the first thing you need to do is you need to graph the functions so you can see the region. You can't determine the area of the region that you're asked to find unless you see the region and you know what the region looks like. So here's the graph of f of x equals x plus 2, and here's the graph of g of x equals negative x squared plus 4x plus 2. So we're trying to find the area of the region that's bounded by those two graphs. Well, the region that's bounded by those two graphs would be this region right here. Okay, next I would sketch in a representative rectangle. And I'm going to use a vertical representative rectangle. Notice, no matter where I decide to put the representative rectangle, I could put it here, or here, or here, or over here. No matter where I put it, function g would be the top curve, and function f would be the bottom curve. So I'm going to opt to just kind of put that representative rectangle right here, and I kind of shade it in a little. I label the base of the representative rectangle, it's delta x, and then I label the height of the representative rectangle. The height of this representative rectangle is the top curve minus the bottom curve. So the top curve is negative x squared plus 4x plus 2 minus the bottom curve. Put that in parentheses, quantity x plus 2. So now once I do that, I can write a definite integral that represents the area of the region that's bounded between the graphs of f and g. So I write the integral. See, my integrand is, well, let me say it again, top curve minus the bottom curve. Oh, I need to determine the limits of integration. So to determine the limits of integration, I could use, since I probably graphed this on my graphing calculator, I could try to use the intersect command and hope they end up being really friendly numbers, which they are in this example. But let me show you the algebra. Let's review the algebra way of doing this, because this will be important when we don't have friendly numbers, or maybe when we have trig functions involved. So we want to find these points of intersection. Remember, to find points of intersection, we just set the functions equal to each other. So we just take negative x squared plus 4x plus 2 equals x plus 2. Okay, I would subtract x from both sides of the equation, and I would subtract 2 from both sides of the equation to get negative x squared plus 3x equals 0. I can factor out an x on the left side of the equation, and then I can use the zero product property to set each of these factors equal to 0, and I get x is 0 or x is 3. Now that tells me the x coordinate of those points of intersection. I know this point of intersection has an x coordinate of 0. I think the y coordinate would be 2. And this has an x coordinate of 3. And I believe the y coordinate would be 5. We are only interested in the x coordinates for the point of intersection. And that's because our integrand is a function of x. We're integrating with respect to x, and I used a vertical rectangle. So I know the limits of integration are 0 to 3. And now it's a matter of just doing it. Let's get an antiderivative, use the fundamental theorem of calculus. So I would, well, first I would clean up my integrand. Let me put the integrand inside square brackets. So I have a negative x squared, 4x minus x is 3x, 2 minus 2 is 0. Now I get an antiderivative. So remember, an antiderivative for negative x squared, I would add 1 to the exponent, put that new, the reciprocal of the new exponent out front. So that's a negative 1/3 x cubed. New exponent for x would be x squared. The reciprocal of the new exponent comes out front, so that's a 1/2. So 3 times the 1/2 would be a 3/2. And remember, using the fundamental theorem of calculus, the 3 comes in first for the x's. So 3 cubed is 27. And 3 squared is 9. Minus, now the zeros go in for the x's. Well, that's pretty friendly. We get 0. And if we take negative 1/3 times 27 plus 3/2 times 9, we get 4.5 or 9/2 as being the area that's between functions f and g. So here's what I want you to do. I want you to pause the video. I'd like you to do, in the exercises, I'd like you to do number 11. Once you've done number 11, restart the video, and I'll be here at the chalkboard working through it to make sure you did it correctly. All right, in number 11, you were asked to determine the area of the region bounded by the graphs of y equals 3x squared and y equals 6 minus 3x squared. So I've already gone ahead and sketched the graphs of each of those functions over there to the right side of my chalkboard. And next I would put in a representative rectangle. Notice, on the region, on this region, this is the region that's bounded by those two graphs. No matter where I put that representative rectangle, no matter where I put it, 3x squared is the bottom curve, and 6 minus 3x squared would be the top curve. So it doesn't matter where I put the representative rectangle, so I'm just going to arbitrarily put it here. The base is delta x, then the height of that representative rectangle is the top curve, 3x squared, 6 minus 3x squared, minus the bottom curve, which is 3x squared. Okay, I know I need to get points of intersection, specifically the x-coordinates of the point of intersection. So if I set the two functions equal to each other, I would add 3x squared to both sides of the equation, divide both sides of the equation by 6, take the square root of both sides to get plus or minus 1 is equal to x. So I know the x-coordinate here is a -1. I don't care what the y-coordinate is. And I know the x-coordinate there is 1. I don't care what the y-coordinate is. Those numbers give me my limits of integration, so now I can write the definite integral. It's the integral from -1 to 1, 6 minus 3x squared minus 3x squared dx. And now it's just a matter of doing it. So I would clean this up to get a 6 minus 6x squared dx. And whoops, I'm going to get an antiderivative. Antiderivative is 6x minus 2x cubed. And use my fundamental theorem of calculus. I evaluate that from -1 to 1. I end up getting 8 as the area. Now you may have noticed, I think I have just enough room right here. I'm kind of squeeze it in to this area right here. You may have noticed that you had the graph of two even functions. Y equals 3x squared is an even function. Y equals 6 minus 3x squared is an even function. We know even functions are symmetric about the y-axis, and our interval of integration is symmetric about the y-axis. So if you notice that, you could have used an old property you learned back in Chapter 5, back in Calculus 1, about when you're integrating an even function on an interval that is symmetric about the y-axis, you could do 2 times the integral, well here I'd do 0 to 1, of 6 minus 6x squared dx. And if you did that, I mean, you're going to get the same antiderivative, 6x minus 2x cubed from 0 to 1. And you're going to get the same value. You're still going to get 8. You know, do you have to use symmetry? Absolutely not. It might have saved a little bit of work. You might have preferred it. But I thought I would just show it in case someone did use symmetry. Plus we got to review an old property from back in Calculus 1. So that was it for number 11. Hopefully you got number 11 correct. So let's head back to the slides and see what is next.
All right, so we did that example, and then you should have done number 11. Hopefully you followed my directions. You paused the video. You put number 11 into your notes, and hopefully you got it correct. Continuing on, let's look at another example. We're going to determine the area that's bounded by the graphs of the following functions. So in part A, the functions are y equals x to the fourth minus 2x squared and y equals 2x squared. Part B, y equals sine x and y equals cosine x. And that's just on the closed intervals 0 to 2 pi. So as always, get this written into your notes because I'm going to head off to the chalkboard and work through both parts of this example.
All right, folks, in this example, we're asked to determine the area that was bounded by the graphs of, and in part A is the graph of y equals x to the fourth minus 2x squared and y equals 2x squared. Part B, y equals sine x and y equals cosine x on the closed interval 0 to 2 pi. All right, so part A. The first thing I would do is I would graph each of these functions. I've already sketched the graph of each of these functions up here. So there's the graph of 2x squared. This big W thing is the graph of x to the fourth minus 2x squared. And I've shaded the region that we're going to find the area for. I need to find points of intersection. So here I go. Finding points of intersection. I set the functions equal to each other. And I'd subtract 2x squared from both sides. Factor out an x squared. Set each factor equal to 0. Square root both sides and I get 0 here. Here I'd add 4 to both sides and then take the square root to get x equals plus or minus 2. So I know the x coordinates of the 3 points of intersection. This x coordinate is -2. Don't know what the y coordinate is, don't care. The x coordinate here is 0. I do know the y coordinate there, it would be 0, but I don't care. And the x coordinate here is 2. Don't know the y coordinate, I don't care. Alright, so now notice this. There are two regions here. There's a region right here, and then there's a region right here. I need to find the area of both of those regions because those two regions together will be the area, it's the region that's bounded by the two graphs. So no matter where I put a vertical rectangle in for this piece, 2x squared is the top curve and the bottom curve is x to the fourth minus 2x squared. The base is delta x. Notice though, no matter where I put a rectangle in here, over here on this region, 2x squared is still the top curve, and x to the fourth minus 2x squared is still the bottom curve, and the base of the rectangle is delta x. I'm going to notice one more thing. These two functions are even functions, and I am going to make use of the property of even functions to find the area here. This rectangle here, let's list the height of this rectangle. It's the top curve, 2x squared, minus the bottom curve, which is x to the fourth minus 2x squared. And notice that's the same height of this rectangle here. It's 2x squared minus the quantity x to the fourth minus 2x squared. So both rectangles must have the same height because we have functions that are even functions. The graphs are symmetric about the y-axis. So the area is equal to 2 times, that doesn't matter, I can find the area of this region and multiply it by 2 to get the total area, or the area of this region. So I can either integrate from -2 to 0, -2 to 0, or I could integrate from 0 to 2. I opt to integrate from 0 to 2. And we're integrating at 2x squared minus the quantity x to the fourth minus 2x squared dx. Oops, give me a little more room. So that's 2 times the integral 0 to 2. I would clean this up a little bit to get negative x to the fourth. Let's see, 2x squared minus a negative 2x squared. That's a plus 4x squared. And get an antiderivative. So antiderivative here is a negative 1/5 x to the fifth. Antiderivative here, well, the new exponent would be 3. The little multiplier out front would be the reciprocal of the new exponent, which is 1/3. 4 times 1/3 is 4/3. And then I use my fundamental theorem of calculus. Let's see, 2 to the 5th is 32. 2 cubed is 8. A benefit of 0 here, it's minus 0. 0 to the 5th is 0. 0 cubed is 0. 0 plus 0 is 0. 2 times 0 is 0. And then when I use my calculator and I do all this stuff, I end up getting the area to be 128 over 15. All right, so that's part A. Now part B, the area that's bounded by the graphs of sine x and cosine x on 0 to 2 pi. So we know what the graph of sine x looks like. We know what the graph of cosine x looks like. We're trying to find the area of that region right there. So let me put in a representative rectangle. Notice, no matter where I put this vertical representative rectangle, sine would always be the top curve, cosine would always be the bottom curve. So I'm just going to arbitrarily put a representative rectangle right there. The base is delta x. The height of the representative rectangle is the top curve. Sine x minus the bottom curve. Whoops. That's an x. Let me try it again. Cosine x. Now I need to find points of intersection. I need to find these points of intersection. Specifically the x-coordinates of those points of intersection. Those points of intersection occur when the functions are equal to each other. When does sine equal cosine? This takes me back to the basics of the unit circle. When does sine equal cosine? Well, in the unit circle, sine's equal to cosine out in quadrant 1 at an x value of pi over 4, and again in quadrant 3, which has an x value of 5 pi over 4. So I can now write the definite integral that will find the area. It's the integral from pi over 4 to 5 pi over 4, sine x minus cosine x, that's the height of the representative rectangle, dx. Alright, so I get an antiderivative. So an antiderivative for sine x minus cosine x. The antiderivative of sine x is negative cosine x. The antiderivative of cosine x is sine x. I need to evaluate that from pi over 4 to 5 pi over 4. So this is just a study in the unit circle. So 5 pi over 4 comes in here for x. The cosine of 5 pi over 4 is negative square root 2 over 2. So the opposite of negative square root 2 over 2, well, that's square root 2 over 2. Minus the sine of 5 pi over 4. Well, the sine of pi over 4 is also negative square root 2 over 2. So minus a negative, that's plus square root 2 over 2. Minus, okay, now pi over 4 comes in for x. Well, the cosine of pi over 4 is square root 2 over 2. So the opposite of that is negative square root 2 over 2. And the sine of pi over 4 is square root 2 over 2. A lot of square root 2's over 2's roaming around here. Square root 2 over 2 plus square root 2 over 2. Yeah, well, that's a 2 square root 2 over 2. Negative square root 2 over 2 minus square root 2 over 2. That's a negative square root 2 over 2. But minus a negative would make it plus 2 square root 2 over 2. Notice here the 2's would cancel out. So you have square root 2 plus square root 2. So the area is 2 times square root 2, or just 2 square root 2. All right, so it's exciting times now that we were able to find the area between two trig functions. So what I'd like you to do right now, I'd like you to pause the video, and in the exercises, I would like you to do numbers 43 and 61. So after you do numbers 43 and 61, restart the video. I'll be here at the board to work through number 43, and then I'll work through number 61. Quick comment on number 43. There's a typo in your book. I need you to change in the book for number 43 where it says y equals 0. I need you to change that to x equals 1. So for number 43, change y equals 0 to x equals 1. All right, so now pause the video, do 43 and 61, and then restart the video when you're done. We'll see how you did on them. All right, folks, on number 43, I didn't write down all the directions, but you were asked to find the area of the region that was bounded by y equals x, y equals 1 over x squared, x equals 1, and x equals 2. Remember, I think the book had y equals 0 here, and I told you to change that to x equals 1. The book has an actual typo there. So I've already gone ahead and graphed everything here. So here's the graph of 1 over x squared. Here's the graph of y equals x. Here's x equals 1. Here's x equals 2. So the region that is bounded by all those graphs, it's this region right here. Okay, notice, no matter where I put a vertical rectangle in this region, y equals x would be the top curve, and 1 over x squared would be the bottom curve. So I'm just going to arbitrarily put my one representative rectangle right here. Its base is delta x. Its height is the top curve, x minus the bottom curve, 1 over x squared. All right, so now points of intersection. Well, they're not too bad here. I just need to know the x-coordinates, the point of intersection. Well, this point has an x-coordinate of 1. We know that from the vertical line x equals 1. And this point here has an x-coordinate of 2. We know that from the vertical line x equals 2. And again, I'm not bothering to write the y-coordinates in there because I don't care about those. They don't matter because I have a vertical rectangle. My height is a function of x. The height of the representative rectangle is a function of x. My integrand is going to be a function of x. So I need to know x's to determine the limits of integration. So here the area is found by, well, let me write down the integral. 1 to 2, the top curve minus the bottom curve, which I would start by just rewriting 1 over x squared as x to the negative second. So I can now use my power rule to get an antiderivative of 1/2 x squared. My new exponent here would be a negative 1. So out front, I would put the reciprocal of that new exponent. That is a negative 1. So minus negative 1, that makes it plus. Evaluate that from 1 to 2. And you know what, before I would even think about doing any evaluation, I would rewrite x to the negative 1 as 1 over x. So the 2 goes in first. So 2 squared is 4. 1/2 times 4 is 2 plus 1/2 minus the 1 comes in. Well, 1 squared is 1. So that gives me a 1/2 plus 1. And this is going to end up being, 1. That was pretty friendly. So for 43, you should have gotten an area to be 1. All right, so bear with me as I erase the board. I'll be right back to do number 61. All right, number 61, you were asked to determine the area of the region that was bounded by y equals 1 minus cosine x and y equals sine x on the enclosed interval pi over 2 to 2 pi. So yes, the first thing we have to do is to graph each of these functions so we can see the region that we're talking about. So I've already graphed. This is the graph of sine x. And here's the graph of 1 minus cosine x. So this is the region that we're trying to find the area for. Notice, no matter where I put a vertical rectangle, in this region, no matter where I decide to put a vertical rectangle, 1 minus cosine x would be the top curve, sine x would be the bottom curve. So I'm just going to arbitrarily put a vertical rectangle about right here. Let me do my normal shading. The base of the vertical rectangle is delta x. The height is the top curve minus the bottom curve. So the area is found, well, this is pretty friendly. My points of intersection are actually the endpoints of the closed interval. So I'm integrating from pi over 2 to 2 pi. The top curve is 1 minus cosine x minus the bottom curve, which is sine x. So we get an antiderivative. So the antiderivative of 1 is x. The antiderivative of cosine is sine. The antiderivative of sine is negative cosine, minus a negative is plus cosine. Evaluate that from pi over 2 to 2 pi. And, well, let's see, I might as well just do this. 2 pi comes in for the x, so we get 2 pi, sine of 2 pi, ooh, that's 0. Cosine of 2 pi is 1. Pi over 2. See, sine of pi over 2 is 1. That's kind of nice. And cosine of pi over 2 is 0. So when I clean this up, well, what do I have? A 2 pi plus a 1 minus a pi over 2 plus 1. So 2 pi minus pi over 2 is 3 pi over 2, and 1 plus 1 is 2. So the area is 3 pi over 2 plus 2. That's it for number 61. So hopefully you got both those correct, 43 and 61. We're going to head back to the slides to finish off this section. You're going to see why for all along so far in this section I've been stressing and saying a vertical representative rectangle. So let's head back to the slides and see why I've been saying a vertical representative rectangle.
All right, as we saw in the last example in part A, I did mention the fact that you could use the concept of even functions, something you learned back in Calc 1. And I actually did, go through that and show that. And then in part B, we were fortunate enough to finally get some trig functions involved. Hopefully you were able to get numbers 43 and 61. Wasn't too bad. Now sometimes, as I mentioned this at the very end of the example, sometimes you're given a function of y. And what I mentioned at the end of the last example, in the last number 61 that you did, was that so far I'd been stressing vertical representative rectangles. And well, now we're gonna look at things a little differently. What if you're given a function of y? I mean, if you're given a function of y, you may, not saying you have to, but you may want to use a horizontal representative rectangle. And I just come back to the basics, folks. Whether or not I'm going to use a horizontal representative rectangle or a vertical representative rectangle, it's all predicated on the key to doing these problems.
And the key is to graph the region. We have to see what we're dealing with, in order to make the determination. So first, you always graph the region. Then you put in your representative rectangle. In the next example, I will illustrate why we want to use a horizontal representative rectangle. And the example is, determine the area that's bounded by f of y equals 3 minus y squared, and g of y equals y plus 1. So as always, put this in your notes, because I'm going to head off to the chalkboard to work through it. All right, folks, this example we're asked to determine the area of the region that's bounded by f of y equals 3 minus y squared and g of y equals y plus 1. We do not have functions of x now, we have functions of y. And I've gone ahead and sketched the graph of each one of these functions of y. This line is g of y equals y plus 1. And this curve is f of y equals 3 minus y squared. Okay, right now you might be wondering, well, how does Bill know that those are the actual graphs of these functions of y? Well, the line's pretty easy. A line is a line. It's a linear function of y. But the f of y equals 3 minus y squared, I could say I graphed it based on my knowledge of conic sections, which I would have done way back in college algebra. Or I could tell you this. With functions of x, for your entire math career, you've been thinking, whenever you see f of x, you could think of that as representing y. Y is f of x. The same thing's true when you have a function of y, except when you see f of y, you could think that's representing the variable x. So you could replace f of y with x. And if you replace f of y with x, you have x equals 3 minus y squared. And I can now solve this equation for y to turn it into functions of x. So if I solve it for y, do a couple of steps at once here. Y squared equals 3 minus x. Take the square root of both sides, plus or minus the square root of 3 minus x. So if I wanted to use my calculator to get this graph, I'd replace f of y with x and then solve for y. And notice I'd have two things I have to graph. I'd have to graph square root 3 minus x and negative, or the opposite of square root 3 minus x. This top piece of this parabola is the square root 3 minus x. The bottom piece is the opposite of square root 3 minus x. And of course I could do the same thing here. I could let x equal y plus 1. I could solve for y, and I get x minus 1 is equal to y. So I would graph x minus 1. That's that graph. So I have the graph. Remember, you see a function of y, you could replace it with the variable x. All right, so this is the region that is bounded by those graphs. Let's talk about why I would not want to use a vertical rectangle. Notice, with a vertical rectangle, if I put a vertical rectangle here, or here, or here, or here, or here, all the way up to this point of intersection. In fact, let me just draw a vertical line right here. If I put a vertical rectangle anywhere to the left of that vertical line in this region, that would be the top curve. This would be the bottom curve. But notice if I put the vertical rectangle to the right of that vertical line. Now notice this is the top curve and that's the bottom curve. We have a different top curve. So if I were to use a vertical rectangle, I would have to put a vertical rectangle in here and a vertical rectangle in here. I would have to set up a definite integral for this region, a definite integral for this region, And the heights of those rectangles would be different because to the left of that vertical line, the line is the top curve. To the right of the vertical line, the top part of the parabola is the top curve. And I would have to have functions of x. Well, I already see the functions of x, but two integrals, seeing square roots involved in the integrands, maybe a horizontal rectangle is the way to go here. So let's consider a horizontal rectangle. Notice, no matter where I put a horizontal rectangle, no matter where a horizontal rectangle goes into that region, now I'm not thinking top and bottom with a horizontal rectangle, I'm thinking left and right. No matter where I put a horizontal rectangle, so let me just arbitrarily put one right here. Notice the line is the leftmost curve, and this parabola is the rightmost curve. That's with a horizontal rectangle. So let me label the horizontal rectangle. Important things. The base of the horizontal rectangle is delta y. And no matter where this horizontal representative rectangle would be, the base is delta y. The leftmost curve is y plus 1. The rightmost curve is 3 minus y squared. That tells me that the height of my representative rectangle that's horizontal. So now let's think. In the vertical case, we take top minus bottom. In the horizontal case, we want to think large to small. I mean, vertically, top, bottom, that's large to small. Horizontal, it will be right minus left. The rightmost curve minus the leftmost curve. Well, the rightmost curve is 3 minus y squared. And the leftmost curve is y plus 1. That's the height of the rectangle. So we find the area by integrating. Well, the height, well, it's the rightmost curve minus the leftmost curve. And since my integrand is a function of y, I'm integrating with respect to y. Delta y dy. Now I need my limits of integration. The limits of integration are found by determining these points of intersection. But here, I don't care about the x-coordinates for the points of intersection. It's the y-coordinates. I mean, it's like, what's the lowest that this horizontal rectangle could go? It's the y-coordinate on the lowest it could go. That's the lower limit of integration. What's the largest that could go? It's the y-coordinate of this point. That's the upper limit of integration. So, but I still find points of intersection the way I always do. I just set the functions equal to each other. So 3 minus y squared equals y plus 1. I'm going to bring everything over here. So I have a y squared plus a y minus a 2. And I'm going to factor that, at least I hope it factors. I think it factors to y plus 2 times y minus 1. So I get y is negative 2 and y is 1. That means this point right here, while I don't know what the x-coordinate of the point of intersection is, and I really don't care what the x-coordinate is, I know the y-coordinate is negative 2. This point here, I don't know what the x-coordinate is, and I don't really care. The y-coordinate of intersection is 1. My limits of integration are negative 2 to 1. Well, now it's just a matter of doing it. I would clean up this integrand. Let's see, it's a negative y squared minus y plus 2 dy. Get an antiderivative of y squared with respect to y. That's a negative 1/3 y cubed minus a 1/2 y squared plus a 2y. And when I use my fundamental theorem of calculus, I'll let you verify this. You put the 1 in and then minus putting the negative 2 in. You're going to get the area to be 9/2 or 4.5. All right, so that's it to this example using a horizontal rectangle. Let's head back to the slides and see what's left to finish off section 6.2.
All right, in that last example, we dealt with functions of y. We saw why it was more beneficial for us to use a horizontal representative rectangle. And, what we need to do right now is kind of summarize everything that we've done in this section. And probably the easiest way to summarize what we've done in this section is, I'm gonna head back to the chalkboard to do this summary. But I want you to pay particular attention to when using a vertical rectangle versus a horizontal rectangle. And I'll highlight this in the summary. And I'm sure I will mention this again at the chalkboard, that everything we're doing in this section is laying the foundation for the next two sections. The next two sections, we're going to start to take these regions in the plane, and we're not going to find the area. We're going to take these regions and we're going to revolve them around a vertical line or around a horizontal line to produce what's called a solid of a volume of revolution. And we're going to find the volume of that solid. So everything we're doing in this section is laying the foundation for the next two sections. So with that said, let me head off to the chalkboard to do the review for everything we've done in this section.
All right, folks, here's a quick summary of what we've done in this section. Remember, when you're asked to find the area of a region, the first thing you want to do is you want to graph everything that's involved. You want to sketch a graph so you can see what the region is. Then you're going to put in a representative rectangle. So I broke it into two cases. If you have a vertical representative rectangle or a horizontal representative rectangle. So in the vertical representative rectangle case, notice that for a vertical representative rectangle, please remember that the base of a vertical representative rectangle is delta x. If the base is delta x, that means you are going to integrate with respect to x. And if you're integrating with respect to x, it means your definite integral is going to have a dx. So, in general, you're going to integrate from a to b. These will be x coordinates. You're integrating from a to b. Here it would be f of x minus g of x. But let me put the even more general case in here. Top curve minus the bottom curve. Dx. And notice, the integrand will be, it has to be a variable in x. Integrand has to be a variable in x to differentiate with respect to x. In the horizontal rectangle case, notice for a horizontal representative rectangle, the base is delta y. If the base is delta y, that means you are going to integrate with respect to y. If you're integrating with respect to y, the definite integral better have a dy. So, to find the area, so here the limits of integration would be c to d. Notice those are y values. And for this picture that I've drawn here, yeah, it would be f of y minus g of y. But let me put the more general case. It's the rightmost curve minus the leftmost curve, dy. And let me go ahead and put this up here. Note the right curve minus the left curve, those are going to be, the integrand is going to be a function, it's going to be a variable in y. So, folks, this lays the foundation for the next two sections. The next two sections, we're going to start taking regions in the plane. And we're not going to find the area of the regions. We're going to take the region and we're going to revolve it around a horizontal line or revolve it around a vertical line and produce a solid and find the volume of that solid of revolution. And the key to doing those next two sections will be to sketch so you can see the region and putting in a representative rectangle and the importance of the representative rectangle. So keep that in mind. Do the process as I've laid out in this video on how to do the area between curve problems. That's it for this video. So now you should do all the assigned exercises in section 6.2. Thanks for watching.